Good afternoon, everybody, and welcome to this year's Jenkin lecture. Our speaker today has a summary of achievements which I need a small iPad in order to memorize. Maybe that's just me and my memory is not getting so good nowadays, but it is an absolute pleasure to introduce Bala Ramamurthy. Bala has some position here in Oxford. He's actually an executive in residence with the Saïd Business School, and he collaborates as part of the Smart Space initiative here in the university. But importantly for this talk, his list of credentials goes right the way back, I believe, to around 2007 in terms of manned spaceflight. I think if we think back over the last 15 years, we've seen the most significant advances in putting people back into space since the 1960s. And it is an absolute pleasure that we have a speaker who's been at the heart of a lot of that activity. He's former director of flight safety at SpaceX and served as launch chief engineer for the NASA Demo 2, the United States return to spaceflight with people on board. He led human rating of the Falcon 9 launch vehicle, co-founded a company called Positron Dynamics to put antimatter to work. Well, it sounds a bit Star Trek to me, but we'll find out more about that, I'm sure. And he also led the design of a lunar lander for the Google Lunar X Prize. He's a recipient of the Karman Fellowship, the Eagle Manned Mission Award, the Dr. Robert H. Goddard Memorial Trophy, and the NASA Exceptional Public Service Medal. He served on a variety of different panels at SpaceX, NASA, and beyond, working on a whole range of technical aspects and engineering challenges, including propulsion systems, rocket explosions. There have been a few at SpaceX, but I'm sure none were your fault. Designing fault detection and response systems, trajectory analysis, composite overwrap pressure vessel quantification, anomaly investigation, reliability modeling. He was key systems architect for the entirety of the SpaceX crew escape system, one of the most important aspects of any manned spaceflight, and made advances across the board in flight and safety to enable the Starship development program at SpaceX, including running the world's first liquid methane, liquid oxygen impact explosion test program. It is with an enormous long list of decades of such wonderful experience that I am absolutely privileged to introduce Bala Ramamurthy, our lecturer for today. Bala, over to you. Thank you very much.
Thank you so much for the kind intro, Steve. Thanks, everybody, for coming. This picture here is a special one, and I think of it as a very optimistic view of what 21st century spaceflight could be. It's sunrise on Mars from one of the rovers that JPL put up there. So jump right into it. Thanks to Steve, to Paolo, as Professor Mark Ventresca, who kind of is the reason why I got to Oxford as part of the Smart Space Initiative, and also to the Karman Fellowship, which is all about international space collaboration. And part of my commitment to that program is to do talks like this and send the message of space out to a broader group. There's citations and details available for all the things I talk about today. Have to thank Wikipedia, NASA, and SpaceX for all this imagery that's in here, and all the teams that worked on it. It takes hundreds, thousands of people to make these accomplishments happen. So, what I'm going to talk about today is what is spaceflight, basically, what exemplifies 21st century spaceflight, I'm going to illustrate that with examples of things that I've done, worked on. I'm going to try and focus on things that you're not going to find in a textbook, things that I've learned from the School of Hard Knocks, and all the information that is in here can be found on the internet, which is amazing. So spaceflight is pretty broadly, just think of it as flying about 100 kilometers, going into orbit ideally, and doing interesting things in space. Some spacecraft go farther. I know this is a learned audience, so I don't need to explain that. But why bother? I also think this audience cares about space, which is why you must be in the audience. But there's certainly a broad number of applications. I know a few of you in the room have worked in areas, for example, Earth observation data. There's obviously the promise of potentially extending human presence on other planetary bodies. And if there's an asteroid headed our way, we need to take care of it. And and ultimately, my motivation in all of this actually was sparked with a deep interest in astrophysics and astronomy. And I was like, I want to learn more about what's out in the universe, and that's kind of what propelled me down this path. So if there was a skeptic here, I would challenge them to tell me how many satellites they consulted with before breakfast. But you can see that there's a huge range of things that satellites can do. Like on the left-hand side, this picture of this building, I think I picked the right one, from Google Images, or Google Earth. And on the other end is, I think it's Arendelle. It's the farthest object, or oldest object, that was imaged by the James Webb Space Telescope. And so the span of things you can do in space is quite, I mean, it's the entirety of everything. So now, no story of 21st century spaceflight is complete without talking about 20th century spaceflight and how that is continuing. We have Voyager that was launched in '77, and it's past the solar system now. It's keep flying. And from an engineering perspective, when you think about that, you still have to keep all the systems that we're used to, understand the telemetry, control the spacecraft, still active today. And in that period of time, whole countries have arisen and fallen, governments have come and gone, all sorts of things have happened since that time. And so this is going to be the story, moving forward as we expand our presence. There's more infrastructure, more satellites in space, and more things we're talking to. We're going to have to remember how to talk to them. Okay, so what a spacecraft is what I'm going to get into next. So you have space, and you have this engineering system called a spacecraft that goes and interacts with that space. And what it can be is it's a pretty big range of things. It can be this, small shoebox-sized thing with literally a tape measure as an antenna, as a deployable antenna. That's it costs less than $100,000. Or it could be this $10 billion giant James Webb Space Telescope that took decades to make, and has, I think, 344, maybe I'm wrong, but 344 single points of failure. So any one of those things fail, any of these deployments, any thermal issues that cause mechanical things to jam up, that would have been a problem. And that whole reason it had to be an origami of a satellite was because it had to fit in a certain size of payload volume that the rocket, the launch vehicle, dictated. So this just goes to show the range of things that exist. And I would challenge people to think about how can we do missions of the nature of the right-hand side with things that look like the thing on the left-hand side. So let's go on to the next one. Now, the perennial question, which is robots versus humans. On the left-hand side is a SUV-sized lander or rover that was landed on Mars, Curiosity. On the right-hand side, my friends Bob and Doug, who I launched to space, and that's them in the Dragon capsule. And the Dragon capsule, I've been inside it. It's like a comfortable SUV inside, and you can think about how do you. If you had millions of dollars to play with, if you're an space agency, which thing do I choose? Do I choose to send robots or people? At first, earlier on, when I was in college, I actually was really into the robots part of things. I thought it was somewhat unnecessary to send people if you could send so many robots for much lower cost out to space at higher risk levels. But then, as I got into the industry, I began to get more and more interested in human spaceflight. I thought of it as you're making this little simulation of what Earth is, what your personal bubble is, and you're sending it to space and you're trying to sustain it for a long time. It was a very interesting engineering challenge. And trying to do that in more and more contexts, farther and farther away, just gets more and more interesting. Did I skip? Sorry. Okay. No. So yeah, how it all began. So you have the International Space Station, which I'll talk about more in a second. But I mean, in order to build that huge multi-billion-dollar facility, you really needed rockets that are capable of carrying large volumes that could then be assembled. You needed people to go with it to help assemble it and start operating it, repair it. And that vehicle was the space shuttle that enabled that. And the space shuttle was around for a long time. So we start, the 2000s, 21st century. 2003, Columbia breaks up. Very tragic event, kills 7 astronauts. What that highlighted was a fundamental design issue of the space shuttle in that its heat shield was exposed to debris strike, and that could cause problems later. And people managed that problem and figured out ways to continue flying the space shuttle for a little while, but quickly became costly, untenable. People thought we need to go to a new design. There were other fundamental issues of the space shuttle, and also the big issue was that it was very expensive. So NASA started this Constellation program, and that's about the time I started my career. And that was the first program I worked on, which was intended to be the US's return to human spaceflight. And the space shuttle was retired after that program was started, but as part of that program, there was a small side program within it. It was called the COTS program, or the Commercial Orbital Transportation Services program, which is intended to be the way in which NASA would send supplies to the space station, take the garbage out, and stuff like that. But it was supposed to be the small side thing, and SpaceX was one of the companies that won that contract. So I'll intersperse here a little bit, so how I intersect this journey. So I started my career at NASA Ames Research Center. My first job out of undergraduate school, I was helping design thermal protection systems, which we'll talk about a bit later. That's kind of the fundamental systems needed for planetary entry and to be able to survive and protect the capsule. I then kind of shifted focus into this engineering risk analysis group, which was doing something pretty unique. It was in the advanced supercomputing group. We were trying to model explosions and try to see what would happen to a spacecraft capsule with the view of designing an escape system. So in the introduction, Steve mentioned the escape system work, and we'll talk more about it, but I was working on some of the analysis that went behind how you might design that system. How do explosion loads look like? The Constellation program ended. I was kind of figuring out what to do next. And I ended up working on this Google Lunar X Prize team. It was a chance meeting in Palo Alto. It's a very Silicon Valley experience. And I became the lead systems engineer of this project where we were trying to build a privately funded lander. And I'll tell you more about that. But then I did some work on the risk of creating a Mars base. And that plot is simply an output of an analysis I did where I kind of assumed that if you had a cost constraint, you only could spend X many dollars a year on the Mars program, and you had different levels of maturity getting into that program, what would be the cumulative number of, every couple of years, Mars gets in a good position where it's easier to send stuff there. So how many of those tries would it take to get to a certain probability of being able to have a sustainable settlement there, and by which I meant, obviously it depends a lot on the definition, but what I meant it as, you are able to send people there and get them back. And it was an interesting thing to analyze, and it kind of suggests that, you should try flying missions and gain experience, which is in hindsight not that big of a takeaway. Should have been obvious. But I joined SpaceX. I worked on the Dragon program at first and Falcon. I was in the mission control for the first mission. The Dragon went up to the space station to deliver cargo. And and then I sort of towards the latter part of my career, I was the chief engineer for the first human spaceflight mission. And I've kind of hit on this theme a couple of times up to this point, which is the problems play out in the space engineering realm in different timescales. There's a picture of me sitting in the corner of this giant flight readiness review just to represent the massive number of meetings and reviews that you had to go through to get to the point of flying people. So that it says problems play out on the years timescale for programmatically. You have missions that play out typically in human spaceflight at least days to months. Astronauts are up there for 6 months, 9 months, or it could be a shorter mission. You have decisions that have to happen in the scale of hours, it's just the launch countdown. And then you have decisions that happen in seconds or less than seconds, and that's the crew escape system. And that's just to contextualize all these different timescales you have to play with. Now, the cool thing, the space station's been around for there's 22 years plus of people who are constantly up there, about 400 kilometers up there. They're just there all the time. Like the people get sent there, they come back, they do experiments there, they sleep, eat. That's pretty cool. But key to sending up such a big piece of infrastructure like that, everything can come back to this one equation, which is the only equation I've shown in this presentation, which is the rocket equation, the Tsiolkovsky. It's a very simple derivation. I'm sure you've all done it. And I mean, really, it all comes down to this. It's like, how fast can you shoot the particles out of your rocket? What's the dry mass of your rocket? And how much fuel do you have to burn? Like, that's it. Like, every optimization that we tried to do is around making this better, like getting the maximum delta V, as we call it. And so, yeah, and I guess what that signifies is mass is very important. Mass is very important, and there are a few other things like mass, power, volume, et cetera, but mass is like the most important thing. If you can take lots of mass to space, you can get more creative, do more interesting things. But sending more mass up costs more. Maybe it's more launches, maybe it's a bigger rocket. So it's all about this equation. And as a systems engineer sitting in the midst of all these decisions, controlling like what the mass of different things are is like really key in how you trade them. So that brings me to the craft of systems engineering. And it's like requirements negotiation, being able to identify your constraints and make trades. Like it's all about trades. And I think of it as the synthesis of a good engineering design. And being able to have different teams, let's say like an avionics team and a structures team, being able to trade off between them, what capabilities you want, what mass does someone get, et cetera. What makes spaceflight very interesting for me is the fact that you have to build these systems to operate in different environments. And the more challenging the environment, the more interesting it is to me. but in order to do that, you really have to understand you have to understand how well you know about the environment, how well can you model it. Like, for example, do I know the atmospheric density and how that changes as a function of like solar activity? Like, have I accounted for that in my design of the forces that are acting upon my satellite that is in orbit? So understanding loads, drawing a simple free body diagram is often very helpful. So there's a big focus on environments, and you'll see why in a little bit with some more examples. I like environments for design and development that are hardware rich, and SpaceX definitely took that principle. And by hardware rich, I mean basically having the ability to, you have lots of engines to choose from to pick for your flight, or you have multiple rockets to pick from. And this helps you make decisions better, or having facilities to do certain kinds of experiments. The trading of margins that I talked about, you also have to be careful of not allocating too much margin or doing it in a way that's heavy-handed, because that might bloat your system, and then it becomes massive, and so it's important to manage that. I have a couple of interesting things that I observed that found are interesting analogies. I don't know how many of you have been to Greenwich Observatory. There's John Harrison's, I saw this when I was 24 or something, and I was walking around and I saw this, the Sea Watch, the chronometer, and there was these big machines, and then suddenly it jumps to this pocket watch kind of thing. And the point of that is, suddenly it's why can't I just use a watch, basically, or modify it to do that? And to me, what that means is I think of it as simplifying, starting with a simple design is actually the best way to do it. Do the simplest design that provides the function you need, and then you layer in robustness. This is I don't know, I enjoy this analogy, but it's okay, if you have a keyboard and the key buttons start going out, if you can still type SOS, you want your system to work that way. You want it to degrade in a way that you understand. A friend of mine likes to say it's you have to design your system to fail in knowable ways. Why do I talk about failure so much? Because things break. They break a lot. And it's basically, you're successful if you're able to figure out what breaks and the solution to it in the available time. And you have to use all the tools that I talked about in your disposal to solve the problem. And real failures are complicated. They're often path dependent, And all the basic stuff you can read in textbooks, go to the internet, learn about it. And so the industry, space industry at large, has figured out all the basic problems. So now all the new problems are the really hard ones. They're like, okay, I exposed a material to a certain type of thermal stress, then I vibrated it, then something broke. And I don't exactly know when it happened. It's that kind of problem that happens again and again. You have to get really good understanding what types of data and what types of testing, which we'll talk about more, to get a good grasp on the problem. And the other thing is, like, if you're trying to do things like you want to send more mass, more rockets, more frequently, more satellites, you have to have this ability to deliver uncompromising quality, but because it's very unforgiving. Like, the rocket will blow up if the loads on it are too high, right? So, but it has to be done cost efficiently. So that is leveraging all the modern tools. And you have to sweat the details. This is like a remove before flight tag. I'm sure you've seen it, planes, rockets. And sometimes people forget to take it off. You have to make sure you take them off. So spaceflight, and this is just a table that shows different latencies and delays, like communication between, I guess parts of the Earth, and then maybe if you're at a different planet or a different part of the solar system. And you can see as you're going farther and farther, effectively it drives you towards having autonomous functions on your craft. You can't send manual commands. So that becomes a very key characteristic of how you design spacecraft is from the earliest days, there were basic features of autopilot. So we get to testing, and you learn a lot more about your system when you break it than when it works. And I strongly believe that. And testing is all about understanding those environments that I talked about. And the more environments that are relevant that you can test it in, it's better. Sometimes you will test something and then realize that your whole understanding of the problem was wrong because you looked at the data the wrong way. Or you might be doing a test and figure out, there was an example where we had a pressure vessel that exploded that I'll touch on later. And we had a whole theory about how solid oxygen caused the explosion. And it was completely wrong. It was simply a correlation in the testing that it happened to explode in this test, but it was not the right reason. And we found out about it because we were doing a test on it, and after the test, we had a camera looking into this pressure vessel, and we were heating up the test rig to get it back to temperature to access. And then we just left the camera rolling, and then when we went back and looked at the data, we saw that the pressure vessel buckled under the exposure of heat from this purge. And then that made us think, wait, why is that happening? And that led to the correct explanation, and that was simply an afterthought. So you have to constantly be on the lookout for these kinds of opportunities to learn. And it's also important that, to me, the most freeing assumption is to understand that your testing is always going to be incomplete. Whatever you try to do, until you actually fly the rocket in the environment or the spacecraft in space, you can't simulate every aspect exactly. So when you recognize that, then it's freeing in a way because now you know the limitations and you know what kinds of tests you want to do. The way I like to do tests is I like to push things to the limit. It's multiple, far more temperature or far more pressure and see where it actually breaks. So it's also important to test at every scale. I have a picture in the top right, which is NASA's whole test program around Saturn V Apollo. They had basically these subscale crew escape tests where the rocket would launch and they would see if the crew escape system would work. And that was an inspiration for some of the testing we did at SpaceX. I don't know if that video will play, but we'll move on to the next one. What the video is a arc jet test, so subscale testing of thermal protection systems that are essential for capsule reentry. So you should conduct testing at every scale. It's not exactly rocket science. The point of this is that there's lots of industries that have made many advances over the last 50, 60, 70 years that we can learn from, and we have. Air traffic control does a pretty good job routing planes around. Can we do that job pretty efficiently for rockets in a similar way? Production lines for cars have existed for a long time. Can we apply those principles to production of rocket engines, components, rockets themselves? Could we use a touchscreen in a capsule that is used in an electric car? And then this diagram might not be super visible, but what it is the continuous integration and deployment strategy in software I mean, obviously you should use that in software for spacecraft too, but can you actually think about using, what would that look like in hardware? So it's all these kinds of influences that, over the last 10, 15 years we've been, integrating into the space industry. And production rate and reliability are interrelated. Left-hand side, there was a lot of ruckus about this strategy that we were using, and there's an article about it that you could read about later, where the Dragon capsule we were using, non-radiation hardened avionics materials. So avionics can be subject to particle hitting and flipping a bit from a 0 to a 1, vice versa. And then that corrupts sort of your system. And so electronic piece parts, we were using automotive parts because they're produced in mass quantities and they actually had pretty good reliability. And if you architect the system to recover from the softer faults, it's actually okay. And the graph above it, it's from a NASA paper, is simply that design choice of using a commercial off-the-shelf set of electronics is a massive improvement in price if you can make the reliability work. On the right-hand side, for this production volume question, if you can actually churn out rocket launches at that scale, and this is, I got it from Reddit, but basically it shows the SpaceX launch cadence, and how that changed over the, 2016 to 2023. I mean, the first year I worked at SpaceX, we launched one rocket. Or actually, yeah, it was the year after I joined that we launched a rocket. But and this year we've launched, or I say we, but I was there recently, 65 rockets. And the important thing there is how that helps reliability is that every time you fly it, every piece of data you get, every learning you get from analyzing the rocket after you recovered it is improving the overall reliability of the system. So you want to make systems robust. Left-hand picture is a good illustration from a recent launch where you can actually see the engines that have failed. Right-hand side, top right picture is from a paper from a colleague at Rocketdyne that has to do with the catastrophic fraction and the probability of failures of engines. So when we talk about making engineering systems robust, if you can design reliability in by having these features if you lose an engine, you still should continue on with your flight. You have the ability to do that. Aircraft certainly can make a landing if they lose an engine, if they're a twin engine. But in order to do that, you have to make sure that most of the time the failures are kind of benign and they don't explode the whole rocket. And bottom is some excerpts from a paper I wrote that had to do with we used physics-based analysis, a transient model. You had the whole rocket engine simulated and tried to create different conditions in terms of temperature and pressure and different combustion volumes to see which of the failures would be rapidly propagating and which would not be. And that gives you some understanding of what the system might do. But the best way to gather this information is actually testing it. I'll touch briefly on software. I have already Linux, C++, everybody uses it. And now that we can use that in spaceflight too, that one of the most practical, useful things of that is we get really good engineers to work on it because there's just so many people who know how to do this. The availability of simulation tools, I've brought up simulation multiple times. The ability to build digital twins of your actual situation in space allow you to better test and deploy your software and operate it. Sometimes, we joke the spacecraft was the platform on which the software ran, basically. But the key to that question about environments is you need to also build these systems where you test with hardware in the loop. Your ability to test the software in conjunction with the hardware sometimes reveals things that you did not think about before. I'd also encourage reading this digital Apollo book. It's really good. And then there's a SpaceX Ask Me Anything on Reddit, which is pretty interesting if you want to learn more about software. I'm going to intersperse here another project that I worked on, which is the Lunar X Prize. And this was right before I was at SpaceX. But basically, this is to illustrate tying together some of the things we talked about. Basically, we were designing we had an open source team that worked in hacker spaces. We designed to fit the spacecraft on a Falcon 1, which is the smallest rocket and hence cheapest at the time. We designed a direct trajectory of the moon. We had storable fuels so we could actually transport the thing to Kwajalein, where it's in the Pacific Ocean, where they would launch Falcon 1 from. We used radio telescopes for ground stations. The Microsoft Kinect had just come out, and the speckle pattern system, we were trying to use that for hazard detection to detect lunar terrain in the landing profile. And so we were able to use lots of off-the-shelf hardware, available software, open source tools, and design all of this with an international team. And now we competed for the prize, our team folded, but nobody actually won the grand prize, which was 30 million. And what was interesting was all of this design was driven by the fact that, okay, the prize was 30 million, so we were like, we shouldn't cost that much more than that. We wanted to break even. And so the challenge was could we get the whole design and mission done for 30 to 50 million? And that's what led to all of these innovative ideas. The bottom right is also an example of how we might gain more experience testing on Earth by piggybacking on an Earth-based lander system that we would shadow mode run our guidance and navigation system. But I think the closest thing that came to this kind of design working was Chandrayaan, the recent moon landing by India. This segues into reusability. Landing was a very important problem to solve. I would urge you to read colleague Lars Blackmore's paper. He's a Cambridge man, but you can see the top left. There were various attempts at landing over time, and we had to increase. So this whole launch cadence thing is possible if you don't have to make a rocket every time. And it's quite foolish to just throw the rocket away. So that was the whole operating principle. And so in order to do that, you have to recover it. But to recover it, you need to have precise landing, because if you're trying to target something in the ocean, it has to land on that thing. Or if you're targeting the pad, it has to land on the pad. And so, in the past, the landing precision was quite bad. It was the bottom left plot shows the various Mars landings, and each of those were kilometers of error. And you have to get it down to meters or less than a meter. So so this was an enabling achievement at SpaceX. Now, as we worked through all of those things, we had to get to, flying people. And then I think about this as the limits of materials versus the limits of the human body. Right-hand side, you have a picture of the acceleration requirements, which is one of the numerous human physiological requirements that you have to protect the astronauts throughout ascent and entry and any part of the flight. People can't be subject to more than a certain number of G's of acceleration or meters per second square of acceleration. There are also all kinds of interesting materials, like liquid oxygen interacting with other materials, causing issues that we have to be cognizant and test out. There's engines that have to work where some of the highest temperatures in engineering systems operate inches away from things that are cryogenic, which is very fascinating. And sometimes on the same assembly, there's that massive temperature differential. So you can only imagine the types of problems you'd have with that, and you have to work out. Speaking of temperatures, that's some thermal imagery from Dragon entering with this ablative heat shield. And basically, that's an example of a system that just can't fail. If it burns up, people are dead. So building a crew vehicle. Left-hand side is an explosion. I was sitting in the control room when this happened. Rocket blew up. I registered the rocket blew up, and I saw a fragment of the rocket flying towards the camera. And we later reconstructed that whole event happened in tens of milliseconds, intact rocket to complete exploded. And we traced that back to a composite overwrap pressure vessel that I mentioned before. And that's just an article in Verge where Elon is talking about how, or Elon Musk, our CEO, is talking about how we had designed the most advanced pressure vessel to solve that problem. And I would contend we did. We basically applied those principles of testing, subjecting the new pressure vessel to every possible temperature and pressure excursion, every type of loading condition, because we needed to make sure astronauts would not die. Because this was it's very hard to escape from something that is happening so fast. But nonetheless, we have an escape system, which we'll talk about more in a second. And I was privileged to work on this program where we got to test a whole rocket. In our mind, we had to test the thing as close to the end condition as possible. And so we had a lot of rockets. We were hardware rich. And so we were like, why don't we test with the full-on rocket, launch it, so we get the aerodynamics exactly as it would be in the case where the engines fail and expose this failure, and have the actual detection systems like trigger the escape and have the whole sequence play out. And so we got to do that. That was the moment when I was confident that we could fly people in space. The other challenge, like in developing these systems, is if you're trying to do it at high cadence, you need money to do it. You need to be able to have commercial customers. That was our model. And that meant we had to consistently keep flying. And so one of the challenges I had to work on was like, how would we introduce the changes necessary, and we acknowledged there were changes necessary to fly people over the course of time while continuing to serve all these other customers. And we came up with these methods of block upgrades, which are common in other industries as well, of like, collecting the changes and introducing them at strategic points in the development program. This is an example of one of those missions. The most significant one was called Block 5 of Falcon 9. And it was the first Bangladeshi satellite, I think, that we launched. But yeah, we basically had a huge, massive number of changes. I was the chief engineer for this one, and basically had to review, like, I'd probably say like 400 significant changes that every one of them had to be thought through, and we had to make sure it was meeting the intent of what we needed to fly people. So I had this chart earlier. The left-hand side's a paper I co-authored back at NASA Ames, but then it came in handy at SpaceX because I was able to apply it actually in real life. And I'll play this video. This is the test that I was just talking about effectively. But yeah, my whole design philosophy here, that I work closely with the flight software team and the guidance and navigation and control team, and almost every team on the rocket, because this is such an integrated problem and capsule. Basically, my whole philosophy was like, we have to design the system, the detection system, in a way that we try to use the most high-level indicators of vehicle dynamics behavior to detect the failure, because we didn't want to. The main counter concern is that okay, you want the system to protect astronauts, but you don't want it to create a false positive escape, because it is an unpleasant. It's a very unpleasant ride. And fraught with risk unto itself. So we had to design a system that would detect most of the time, with 95% of the time with 90% confidence. We'd had to show with simulations and analysis that throughout the entire ascent corridor, which is like the whole coast of the US through like Ireland, that the capsule could land anywhere in that whole stretch. Basically, we had to have escape capability covering that whole period. And we were able to show that through analysis using 6 degrees of freedom simulators of the trajectory. That meant I had to come up with ways in which the rocket would fail and think of like comprehensive ways to show that that analysis closed. And one of the other principles was like try to use sensors that are already on the rocket that were used for other normal functions of flight. And we didn't have to add a single sensor that was not used for another purpose to execute this system. Okay, we're getting towards the end of the talk, so I'll tell you the story. So we talked about the decisions that are made on scale of hours. And we had and I want this to kind of tell you how a development flight test looks. So we had this challenge of launching the crew mission by a certain date. We had many other customers to serve, and we had lots of launches to do. We used each launch as a test opportunity. Well, that's how I viewed it, since I was running the crew stuff. Like I wanted to make sure that we learned from every flight. We had a very significant flight where we were testing out a lot of the crew systems. And in the course of the countdown, I was taking a nap in a conference room, and I get called, because the mission was later at night, and I get called, and someone tells me that a component is broken on the rocket. And the problem with that is that component was, if that doesn't work, you can't conduct the fueling sequence that we'd specifically designed to operationally combat the issues that caused that rocket explosion I talked about a few minutes ago from occurring. So we needed that component to work to proceed with the countdown. So I was like, well, let's take the component off. It's broken. We're sending the commands. It's not working. We see no responses. Let's take it off. And then I was like, well, if there's some chance we figure this out today, we should prepare for it. So we went into the hangar, tried to find another rocket that had the same component, found one, and put it back on the rocket. We took the broken one off, and I tried to think of like what's the quickest way in which we could understand what's wrong with this component. And this is, of course, is not that component. It's a webcam, but it's an example of an industrial CT scanner. So I knew that the launch facility we were at had a materials lab. I knew they had a CT scanner, so we got the guy to come run CT scan of the part to see if we can literally like X-ray our way through the problem and identify the issue. Didn't, and so we had to then move on to the next step. And this is all to show like kind of the triage that you have to do in this sort of environment. And bear in mind, the clock is ticking. We have a launch that's coming in a few hours, and we have to solve this problem, understand it fully. So we're like, okay, let's take it apart. Now, the technicians at the site did not know how to take this type of part apart. So we created a teleconference with the people who knew how to do it, taught them how to do it. They took the part apart, and then they found a sticky substance. And we're like, okay, at least we found the approximate cause. There's a sticky substance. So now we had no understanding about what that was. So I asked NASA during the countdown, I was like, can we have someone run a Fourier transform infrared spectroscopy on this thing to understand what the material is? Then that might give us a clue as to where it came from, because it was not supposed to be there. So they found a material scientist in the launch audience that had congregated to watch this launch, brought her to the materials lab. I sent my team member out there with the sticky residue. We analyzed it. With the spectra shown that it's basically a type of glue. It is a very unexciting finding. It was a type of glue. Then we came up with an understanding of how that glue would have gotten to that part, even though it had been tested before. And it had to do with thermal cycles, et cetera. And we arrived at a whole set of understanding in the hours leading up to this launch, which is, I think, I learned about the problem maybe 8 hours before the launch, and like 2 hours before, or an hour before the launch, we had this sort of resolved, like this whole story. And meanwhile, there was other stuff going on. You have to also manage, and this is like in an operational control room, like you have to manage this whole activity, which is unusual, along with all the normal activities of making sure everything else is fine. For example, we had our booster recovery team out in the ocean, and they had pretty bad seas, and we briefly lost communication with them. And it was like, are they okay? So it was like managing all of these things in parallel is a pretty interesting skill to develop, and you're doing systems engineering. And what I'm particularly proud about this story, because we didn't take any shortcuts. We did all the things. We just did them really fast. And so, well, once we'd identified what the issue was, we had to make sure there were no other components on the rocket that were of the same type that had the issue. So we wrote software, tested it, deployed it, and tested all those components. And then we got to launch it. That picture, I don't know, it's hard to see here, but in the middle bottom is from the beach when I was drinking champagne later. But it's the plume of the rocket through the layers of the atmosphere, which is kind of cool to see. That remains up there for a little while after the rocket's launched. But we had a successful mission, and it was awesome. Yeah, and now we have private astronauts flying. Like SpaceX flew like 38 astronauts or so. Like lots of astronauts have flown and come back. I'll touch on a few other things. I know we're getting close to Q&A time. But Steve had mentioned the positron dynamics company. And I just want to throw out a couple of these ideas as, we've talked a lot about the spaceflight that has happened. What are some ideas that can happen in the future? And one of the ideas I worked on was like, okay, let's take that rocket equation. Let's see, how can we maximize what the exhaust velocity is, or the specific impulse? And the most energy-dense material in the world is antimatter. So a couple of friends and I, on it just for fun, we were like, let's start a company. It ended up getting investment, and we had to do a bunch of experiments. But basically, there's a paper in the Journal of the British Interplanetary Society. That's where that picture is from. And we did a couple of studies for NASA. But basically, the whole idea was like, if you really want to go past the solar system, you need something like antimatter, the energy density of it, to, like, say, catalyze fusion and create really fast particles that allow you to propel a spacecraft and achieve these really high exhaust velocities so you can efficiently burn fuel. And the bottom right is a trajectory, a pretty circuitous route through the solar system, bringing an asteroid back to Earth that I did an astrodynamics analysis on. But basically, this is just to provoke thoughts on, like, how else could you, once you've optimized the mass, like, what else can you do? You can shoot particles out faster and see if you can go, get higher delta V through that. Another sort of idea I worked on, this was actually from the right-hand side pictures from a planetary science conference that I presented this at earlier this year, has to do with, like, how can you leverage the environments that space offers to you, or like a planetary body? And this whole idea was around, like, how do you beat the endurance record that the last Venus lander had set? And that was this Russian lander. It was about 2 hours, but the environment on Venus is so harsh that electronics die, and basically your craft is dead. And so this whole idea was around, like, could you have the brains of the satellite on orbit in a constellation of satellites that's, maybe they can have spectrometers, and maybe you can dope the ablator, the ablative heat shield, with certain, chemistry that interacts with the atmosphere to detect certain particles or detect certain composition, and look for those signals from orbit. So you don't have to worry about getting those electronics working in the harsher environment. And then once the ablated layer goes away, like, can you use those little cores of what's left over as this, leverage piezoelectric effect and try to, create these little sensors, RF beacons, and create this, set of dispersed RF beacons. So essentially, the overall thought here is, like, we should think about, I encourage people to think about new ways in which we can use the space environment. So this brings me to the last slide, which is really, if you wanted to work on something in this industry to push it forward, what would be the interesting projects? And I'd say, like, in situ resource utilization. I mean, we can pretty efficiently use solar energy in space to power the spacecraft, but it would be really amazing if we could actually do stuff with the materials that's available in the planets we're going to kind of propel or enhance the mission that you're on, or push the mission forward to the next location. Like, if you could harvest fuel from the places you're going to, and you could propel that spacecraft to the next location. In fact, like, for example, like SpaceX's choice of methane for Starship is not accidental, right? It's based on, well, you could potentially create methane fuel on Mars. So constellations and swarms of satellites, they're all in the news and everybody's talking about them, but they do provide a very interesting way to manage reliability, to be able to have more dynamic ability to configure certain capabilities. And so they remain pretty interesting. I also think they'll happen on the moon. You'll have rovers, like groups of rovers, like being able to cooperate and work together. As we expand and go farther out, deep space communications becomes more important, like creating relay satellites. I strongly believe in the fact that because the inverse R² issue and having to go farther, you will need to have some kind of nuclear reactors in space if you want to go farther, especially if you want to process materials on an asteroid and bring it back to Earth or something. Propellant depots and transfer, being able to manage propellants on orbit to fuel up a rocket in space and move it to a different location, they're going to be more and more important, especially if you're talking about moving vast quantities of mass to say like Mars or anywhere else. And that also brings up the question of controlling large spacecraft. The space station is a pretty large spacecraft, but let's say you want to have a space station that simulates 1G gravity. That's a lot of angular momentum that you have to deal with. And then lastly, I'd say there's a lot we can learn and apply to terrestrial engineering problems from this approach of design and test iteration, the quality and rigor that's necessary to execute human spaceflight, and then the rapid spiral development process in general. With that, that's a conclusion of my talk, and we'll do some Q&A.